Okay, so in our last lecture, I have given you an overview of black holes, and in this particular lecture, I would like to discuss certain very unique features of the Schwarzschild metric. So, before I talk about the Schwarzschild metric, let me just a little bit talk about the gravitational collapse. Well, you see a massive star, right? It undergoes continual gravitational collapse. When? That is when its nuclear fuel is exhausted. And then what happens is that it undergoes a continual gravitational collapse. Now you see there are three types of super dense compact objects that can be found when such a thing happens. Three types. What are they? The first is white dwarf, second is neutron star, and the third one is the black hole. Okay, now let's start with the white dwarfs. Well, white dwarfs, they are basically supported by degenerate electron pressure, right? And they have mean densities of the order of 10 to the power 5 to 10 to the power 6 gram per centimeter cube. So this is the order of their densities, and here basically the ongoing gravitational invasion. So if this is the gravitational force, or then this one, there is the degenerate electron pressure, and as a result of this, when there is an equilibrium, we have hydrostatic equilibrium in this case, and then we have this white dwarf, right? Now you see these white dwarfs, this thing, it will not happen that it will always be like this. What I mean to say is that these white dwarfs, they have a maximum mass limit, and this is known as Chandrasekhar mass limit. If the mass of the white dwarf is greater than this Chandrasekhar mass limit, then what happens is that the white dwarf, which is supported by the degenerate electron pressure, that means the pressure of the cold degenerate electrons, they cannot be in equilibrium, and what happens is that this becomes dominant, and as a result, a star whose mass is above the Chandrasekhar mass limit, it falls to collapse as its internal pressure fails to counterbalance the gravitational inward force. Right. Now, what happens next? Well, you see, according to the Pauli's exclusion principle, there is a restriction on the possible number density of free electrons. Now, this compels the excess electrons to combine with protons to form neutrons. And when the nuclear density become of the order of 10 to the power 14 gram per centimeter cube, then what happens is that all electrons, they combine with protons and producing a neutron star. Right. Now, in this state, the neutrons, they become completely degenerate. And you see, you can say that a neutron star is quite similar to that of a white dwarf. The difference is that it is supported by cold degenerate neutrons. Now, similar to that of the Chandrasekhar mass for white dwarfs, which basically represents the maximum mass of a white dwarf, supported by ultra-relativistic electrons. So here also, in this case of neutron star, we will also have an upper limit of the neutron stars. Okay, so this is the scenario. But again, the stars which have mass greater than this upper limit of the neutron star, what will happen for them? The same old story will continue. That means they will undergo continuous gravitational collapse. So, what does it mean is that very heavy collapsing stars they have no equilibrium, right? And so they are always in a state of continued collapse, and as a result the third super dense object, which is black hole, is formed. Okay, and now we are going to study the metric outside the black hole. Fine. So this is the prelude, and now let me talk about the Schwarzschild metric. You see, in general relativity, the unique, let me write it. So, in general relativity, the unique spherically symmetric vacuum solution of Einstein's equation. This is what I mean to say in general relativity. So, of Einstein's equation, right? Just a second. That means this equation. So, vacuum solution by solving the Einstein's equation, and this, the unique spherically symmetric vacuum solution, is basically the Schwarzschild metric. Now, let me write down this metric in ordinary units. So, the metric is 1 minus 2gm divided by c square r into c square dt square minus, again the same old term, 2gm by c square r power minus 1 dr square minus r square d theta square plus sin square theta d phi square. Okay. Now you see, this metric is second only to the Minkowski space in the list of important spacetimes, and I have written here this metric in spherical coordinates. The constant m here is basically interpreted as the mass of the gravitating object. Okay. Now you see what happens as this mass m tends to 0. Well, you see, in this case we recover the Minkowski metric. Right. So basically, you can say that this thing is also possible when, so there are two cases. One is when m tends to 0, and another is when r tends to infinity. You can check this yourself by putting is in this here. This term goes to 0 for r tending to infinity. So even in this case also, when r tends to infinity, the metric becomes progressively Minkowskian, right? And this property is known as asymptotic flatness. Okay, so the first thing that I'm going to talk about now is, what about the singularities of this metric? What do you see? You see these two terms here. Let me write it down. Yes, here. There is nothing over here. This is quite plain. But here you see this term and this term. What do you see? You can see that if you consider this case, what happens when r tends to 0? This term becomes infinite. Now look over here, this entire term, this is 1 by something. Now what happens when r becomes equal to this entire term, this thing? That means this entire term, when r becomes equal to this, then this term becomes equal to 1. So 1 minus 1 equal to 0, and 1 by 0. So this term again blows out, right? So you can say that the singularities of this Schwarzschild metric, how many are there? Number 1, r is equal to 0, and number 2, r is equal to rs, or basically what? It is basically 2gm by c square, right? Now this term is also known as Schwarzschild metric, rs. So r is equal to rs. Now you see, so we have got two singularities. Now this singularity r is equal to 0, this singularity we have also seen previously in the Newtonian theory. So this is basically an essential or gravitational singularity, which is present also in Newtonian theory. Okay, so this is the essential or gravitational singularity, and this one here is a pseudo or spurious singularity. Now you must be wondering why I am saying so. I'll just show you soon. But before I proceed, you must remember that we are calling this singularity because of the fact that this term becomes infinite. That means this one, this term. So this entire term blows at r is equal to rs, that is the Schwarzschild radius, and here this entire term blows at r is equal to 0. So there are two singularities. This one is essential, right? And this one is your pseudo singularity. Fine. Now you see, sometimes this is also called coordinate singularity. Okay. Now in order to decide whether this r is equal to rs is a coordinate singularity or an essential singularity like this one essential or gravitational singularity, it is important to evaluate the scalars at the point. Now, you see, let us consider this R is equal to Rs. Now, you see, all the scalars are finite and also well behaved at this R is equal to Rs, including the Kretschmann Scalar. Okay, now let me write down the value of this Kretschmann scalar. So R u comma rho sigma same mu rho sigma, and you must remember the value is 8 square by to the power 6. You see, R to the power 6. Now this thing, it is finite. So what does this mean? This means that this R is equal to Rs is a coordinate. So shows that R is equal to Rs is coordinate, or you can say removable singularity. Now there are other examples of such coordinate singularities as well. Let me give you an example. You see, okay, now let's consider the Minkowski metric in spherical polar coordinates. So we can write down as, now I am using C is equal to 1 here, and okay, so now you see, at R is equal to 0 and theta is equal to 0, we find that the coefficients of d theta square and d phi square respectively vanish. Here, this one. So, along with the determinant, so at these values, the coefficient of d theta square and d phi square vanish, along with the determinant of G. Let me write it like this: determinant of G u comma. But if we change over to the Cartesian coordinate system, then what happens? You see, then you see this metric then in this case the same metric becomes ds square is equal to dt square minus dz square, right? Now here you see the determinant never vanishes. However, for theta is equal to 0, we have x is equal to y is equal to 0 and z is equal to r. And if r is equal to 0, theta is equal to 0, then x is equal to y is equal to z is equal to 0. Right? Now determinant, you see, is non-zero at both these points. So these are examples of coordinate singularity. Okay. Now let us come back to our original issue. You see, this coordinate singularity at r is equal to rs, it arises due to inappropriate choice of coordinates, and it can be actually and can be eliminated by a change of coordinates. Okay, let me talk in terms of physics. You see, an astronaut falling toward and crossing the surface of r is equal to rs will never feel anything unusual. In his immediate vicinity, the physics will go on in the way as it always does in a freely falling reference frame. Of course, there are tidal forces, and these tidal forces will what? Will become, they will basically grow stronger and stronger as the astronaut falls deeper and deeper towards the center. Right. However, you see, these tidal forces remain finite at r is equal to rs. Only at r is equal to 0 do the tidal forces become infinite, and this indicates the presence of a real physical singularity. Now, let me talk about this first appearance of the Schwarzschild radius. It is quite important, you see, that interestingly, the Schwarzschild radius first appeared in the work of Laplace. In which year, you know? 1798. Now let me just show you the very basic. So let us consider a particle of mass m, which is escaping the gravitational pull of a body. Now this body could be a planet or a star, whatever, of mass m. This is capital M and radius, say, capital R. Now using the Newtonian argument, so the work done to escape is how much? So let us find it out. It is just equal to this. Then this is just this value. Okay? Fine. Now, supposing the light consists of particles of mass m traveling at speed v is equal to c with kinetic energy half mc square. Now, in this case, we may deduce that the light will not escape if G by R is greater than half mc square. That means r if r is less than 2gm by c square. And this is precisely the Schwarzschild radius. So if the radius of a star is smaller than its Schwarzschild radius, it will not shine. Right? Now it is amusing and really odd that despite the gross errors in these derivations, Laplace reached the same conclusion as that mentioned above. Right? Now we may take this argument a little bit further. Let us consider like this. So if the density of a spherical star, if density of spherical star is rho, then from this condition, considering the mass is equal to what? Basically you consider rho is equal to m by v, that means 4 by 3 pi r cube. So if you do this, right, then from this condition what we will get is this relation: r square greater than 3c square divided by 8 pi g rho. So I am basically using this, writing this same expression, okay, in terms of rho. So I am getting this relation. So what does this mean? You see, this means that, so if a star, of course, of given density is big enough, then what? It will not shine. You see, something very interesting. So it is basically possible for the largest objects in the universe to be invisible. To be invisible. Right, very interesting and nice arguments. Okay, now you see what I am going to do. I am going to write this same metric in terms of this Schwarzschild radius, Rs. So let me write down the metric, right? Okay. So basically the same metric is d square is equal to 1 minus Rs by R into c square dt square minus again 1 minus Rs by R again with power minus 1 minus r square d theta square plus sin square theta d phi square. Good. Now you see if r is in the range, what range? That is between 0, r and less than Rs, then the Schwarzschild solution is free of singularities. Right? Okay. However, something very different happens. If, or you can say in the region, in the different region, which region is this? This one. Although it is free of singularities, however, in this region, what happens is that, you see, the value of G00 is what? 1 minus Rs by R, and what is G11? It is just 1 by minus 1 by 1 minus Rs by R. And what's the sign? So its sign is less than 0. And what about this sign? You see, its sign is greater than 0. Thus, you see, these signs are opposite of what they are normally. So, thus, the signs of G00 and G11 are opposite of what is normal. Now accordingly, in the region R less than Rs, what happens is that T is space-like coordinate and R is time-like coordinate. Now because you see the metric tensor here, because you see this metric tensor is a function of R, and because R now measures the progress of time, so it follows that when R is less than Rs, then the metric tensor is actually time dependent. Let me write it down. So, because the metric tensor is a function of R, and because R now measures the progress of time, so it follows that when R is less than Rs, then the metric tensor is actually time dependent. Okay, now let me state this more precisely. So basically in the exterior region, that means R is greater than Rs, the static character of the metric tensor time independent character or time independent or static character, right? Of metric tensor is a consequence of our particular choice of coordinates. Now, if we were to use new coordinates, what will happen? Say x prime mu, that deform in time. With respect to the t, theta, r, phi coordinates. Then what? Then you see, then the metric tensor as seen in new coordinates would of course what? Be time dependent. Right. However, in the interior region, that means R is less than Rs, the time dependence of metric tensor is not a consequence of choice of coordinates. This is important, you must remember. This time dependence is unavoidable, just like the uncertainty principle is unavoidable, because regardless of how the new coordinates x prime mu are defined in terms of old coordinates and advance of time, that means ds square is greater than 0, is impossible unless dr square is greater than 0. So the advance of time necessarily entails a change in R and also change in metric tensor. Okay, so this is very important, this point, that this time dependence, this is unavoidable, and you must remember these arguments. So let me again do a little bit recap. So what I have been saying basically is that in the region R less than Rs, R becomes time-like and T becomes space-like. Right? Now, as the metric depends on R alone, we cannot have a time-independent metric. In this region, so it is always time dependent. Okay, R being the time-like coordinate, being the time-like coordinate, can only proceed towards the future and not toward the past. Unlike a space-like coordinate which can change both ways. Right. So you see, if a sphere is collapsing, then, so if a sphere is collapsing, then after crossing the r is equal to rs, the future direction will correspond to that of decreasing r. Hence, it will go on collapsing and can never reverse its direction, which would then correspond to a change of direction towards the past. Okay. Now, in contrast, you see, if a sphere with r less than rs is expanding, let's see what happens. Then the future direction will correspond to the direction of increasing r, and the sphere would correspond to a white hole. Whereas the former corresponds to a black hole. Now you see, this black hole term was given by Wheeler. And why is it called black? This is called black because you see, nothing, not even light, can come out of it. It is called a hole because if you fall into it, you can neither come out nor communicate with the people outside. Okay, as if it were gone through a hole in our space-time. Okay, now let us discuss the difference. So, the difference introduced by gravity in local time with respect to time at infinity. Now you see, near this r is equal to rs, many things change. Let us now look at the proper time. So this is the proper time, right? From here we can also get this form. Now you see, let me change the color. Yeah. Okay. Now you see, when r tends to infinity, what do you see? Both times agree. So you can interpret t as the proper time measured from the infinite distance. Now, as the system with proper time tau approaches Schwarzschild radius, dt tends to infinity. You see, according to this term, so as r tends to rs, what happens is that dt, it tends to infinity. That means the object never reaches the Schwarzschild surface when seen by an infinitely distant observer. The closer the object is to the Schwarzschild radius, the slower it moves for the external observer. Now this is the difference introduced by gravity in the local time with respect to time at infinity. Now there is another very interesting effect, which is that of redshift. Now you see, a direct consequence of the difference introduced by gravity in the local time with respect to time at infinity is that the radiation that escapes from a given radius for r greater than Schwarzschild will be redshifted when received by a distant and static observer. Now, so let me show you. Now, since the frequency and hence the radius of a photon depends on the time interval, so from this previous equation over here, we can write this expression. Now, what about the redshift? The redshift is basically measured by divided by lambda. So this means that we have from this relation 1 plus z equal to this relation. So we see that as r tends to Schwarzschild radius, redshift becomes infinite. So what does this mean? This means that a photon needs infinite energy to escape. So this means that a photon needs infinite energy to escape from inside the region determined by Schwarzschild radius. Now, events that occur at r less than the Schwarzschild radius, they are in fact disconnected from the rest of the universe. So we call this surface of r is equal to rs, what? Event me write it down. Event horizon. Okay. So whatever crosses the event horizon will never return. And this is the origin of the expression black hole introduced by Wheeler in mid 1960s. So the black hole is the region of space-time inside the event horizon. Next, we will discuss about this cutting off of signals at the Schwarzschild radius. Okay, now to understand how the signals are cut off at this Schwarzschild radius, that means R is equal to Rs, or sometimes we can also use small rs as well. Let us consider a light signal propagating in the radial direction. Now, the velocity of this light signal with respect to the t and r coordinates can be calculated from the metric by putting just d square is equal to 0, and so we will get this relation. Let me write it down here. Now, when the signal approaches r is equal to rs, so when signal approaches r is equal to rs, or let me write it down in small, r is equal to rs, then the coordinate velocity, this coordinate velocity tends to 0. Okay, so let me show you the figure where the forward light cones, which can be obtained from this relation, are there. So here you can see, so what I have done is I have used this relationship which we have just written previously, rs by r. So from here I have shown the values of light cones. So from here, light cones at different r. So this is what you can see over here. Now you see, in the exterior region of the black hole, that means in this region, r greater than rs, over here you see the units is r by rs and this is t by rs. Okay, now in this exterior region, the axis of the light cones, you see this one, this axis, this one, you see this is parallel to the t-axis, parallel to the t-axis. Now whereas in the interior of the light cone, the axis of the light cones is parallel to the r-axis. So here you see axis parallel to t-axis, and here axis of light cones is parallel to r-axis. So axis of light cone. Right, so I have just shown you here. Now you see the strange orientation of this light cone in the interior region here. From here to here, the strange orientation is a simple consequence of the reversal of the character of the coordinates in this region. So r is time-like coordinate and t is space-like coordinate. Now in the interior region also, this quantity, you see, dt by dr gives what we normally call the velocity, that is the ratio of space-like increment to the time-like increment. Okay, so let me write it down. So in this region, it is basically dr dt is the velocity. right? Whereas in this region it is basically dt dr, which is the velocity, right? So this is what I have just told you. I have also told you that in this exterior region basically r is space-like, t is time-like, whereas in this interior region r is time-like and t is space-like. And because of this reversal of the character of these coordinates, we have the consequence of this strange orientation of the light cones. Okay, so you see the strange orientation of the light cones is because of this reversal of the character of these coordinates. In interior r less than rs is because of the reversal of character of coordinates. I am writing down the important points over here. So, okay. Now you see the existence of event horizon at r is equal to rs is obvious from the inspection of the light cones. You see, any kind of signal must necessarily travel in the space-time direction that lies within the light cone. Now, since the light cones in the black hole region inside, now you see light cones in this region are oriented towards r is equal to 0. So, any signal in this region is unavoidably pulled towards the decreasing values of r and can never leave the black hole, right? So let me write it down. Since the light cones in r less than rs region are oriented towards r is equal to 0. You see, they are all oriented towards this r is equal to 0. This is okay, r is equal to 0 over here. So, any signal in this region is unavoidably pulled towards decreasing value of r and can never leave the black hole. Now note that the light cones are tangent to the surface, are tangent to surface. R is equal to Rs, which is this one, the dashed lines. This means that viewed in space-time, the horizon is a null surface. Now you see, this is a general, so this means that horizon is a null surface. Now this is a general property of event horizons. Since a light signal that starts exactly on a horizon and is aimed toward the outward direction is sandwiched between those signals just outside of the horizon which escape outside and those just inside the horizon which fall inward. So the light signal therefore propagates neither out nor in. It hovers in a place forever, and thereby indicates that this place at which it is hovering is a null surface. So this is a null surface, this one over here. Okay, this entire surface is a null surface. R is equal to Rs. Now such a hovering light signal on the horizon of a black hole, we should not confuse it with the signal in a circular orbit around the black hole. You see, the hovering signal has no circular motion. It is completely stationary. Okay, now let me talk about another very interesting point. Although signals cannot emerge from the black hole, they can enter it freely. You see, the curve here is the world line of a light signal that travels inward. And this curve is obtained by integrating the previous equation, that dr/dt term, which we just, this one. Okay, now this signal follows the world line, you see AB, this is inward direction. Let me change the color. So this is inward. Okay, so this world line, you see AB, this follows, the signal follows this world line AB to t is equal to infinity, and then it follows the world line BC here to r equal to 0. So signal follows world line AB to t is equal to infinity, and then BC to r equal to 0. Now as measured in t and r coordinates, the signal velocity tends to 0 at r is equal to rs, and the signal takes an infinite t time to reach this r is equal to rs. Hence, from the point of view of an observer at infinity, whose clocks indicate t time, the signal never reaches the horizon. To make this more concrete, suppose the black hole is surrounded by some dust that scatters a small part of the light signal. So the position of the signal becomes visible to an observer at infinity. Then this observer will see a lighted spot asymptotically approach the Schwarzschild radius even without reaching it. Now, this is in fact a manifestation of the gravitational time dilation effect. So, from the point of view of an astronaut in free fall in the vicinity of the r is equal to rs, no such slowing down occurs. The signal always has the speed of light relative to him. The signal and the astronaut both cross the black hole in a finite proper time. Now, you see, if the observer at infinity keeps in touch with the astronaut by audio and video radio signals, then what? Radio links, audio and video radio link communication. Then he or she will find that the motion and metabolic rate of this astronaut are slowed down in much the same way as the motion and oscillation rate of the light signal. The astronaut appears to go into slow motion, and his movements basically freeze asymptotically. So the last syllable he sends through his radio before crossing the black hole is drawn out to infinite length when received by the outside observer. The words he speaks after that remains inside the black hole. Okay. So let me now talk about the last part, which is, after talking so much about this Schwarzschild metric, now finally you must have guessed that there is something wrong going on near about the Schwarzschild radius when viewed in terms of this Schwarzschild coordinates. So we are going to now highlight this point. So we are now going to talk about the inappropriateness of the Schwarzschild coordinates inside the event horizon. You see, the extra part of the pathway, which is here, right now I am showing a different diagram compared to what I have shown previously, this one. So this is the extra part of the pathway, which is shown in orange. From the horizon to the central singularity, it starts at t tending to infinity and then leads back to the coordinate time to some earlier finite value. See, this is here t tending to infinity, and this is here a finite t, right? Now it's tempting to interpret this as a sign that the infalling observer is traveling backward in time. However, no such fanciful interpretation is needed. Okay. It is true that the value of t is decreasing, but we have already learned that in general relativity, the coordinates lack immediate metrical significance. The decreasing value of Schwarzschild coordinate time t for an infalling observer inside the event horizon simply shows that these Schwarzschild coordinates are spatially poor. So this fact that the decreasing value of Schwarzschild coordinate time t for an infalling observer inside the event horizon simply shows the Schwarzschild coordinates are inappropriate, or you can say the Schwarzschild coordinates are spatially poorly suited to the task of describing the last stages of the fall. Okay. Now more evidence of this inappropriate can be obtained by using them to describe the light cones along the path of an infalling observer. And this we have done here. You see, this is what we have done. So, see here, the light cones, they are progressively becoming narrower. They are slowly becoming narrower. And you see what happens over here. Here, dt dr, it becomes plus minus infinity at r is equal to rs. Right? So, causing these light cones to become very narrow. So, all of a sudden, the light cone suddenly becomes, now you see again broad over here. So from broadness it starts becoming narrower, it becomes very narrow, and then all of a sudden it starts becoming broad again, and their time-like regions become horizontal, so that the only possible direction of radial motion are towards the singularity. Now the tipping of the light cones makes a certain kind of sense, since it indicates the inevitability of encountering the singularity once the event horizon has passed. However, the abrupt switch in direction and the sudden broadening of the light cones looks very odd and is another sign of the inappropriateness of the Schwarzschild coordinates in this region. So, let me write it down. The abrupt switch in direction and the sudden broadening of the light cones looks very odd and is another sign of the inappropriateness of Schwarzschild metric inside the event horizon. That means over here. Now, before I finish today's talk, it is important to note that there are other coordinates also where such type of things are not present. And I will be talking about the Eddington-Finkelstein coordinates later on in my lectures. And there you will see that there is no such behavior of the light cones. Okay, fine. So that's it for today.